The second speaker of today's session is Boshi Yang from Clemson University. He will be presenting his work about convexal results for quadratic programming with non-intersecting constraints. Thank you, Boshi.
Thank you, Carla, for the introduction. Today I'm going to talk about this quadratic programs with non-intersecting constraints. This is joint work with my student Atkinson Joyce at Clemson. What we are interested in this project is that we want to understand the structure of the closed convex hull described here in blue. Well, basically F here is just like any quadratically defined set. It can be non-convex, it can be unbounded. And what we are looking at here is the closure of the convex hull of F in this lifted space. This set shows up quite often in mixed integer quadratic program and in quadratically constrained quadratic program. So just as an example, in a QCQP problem, you minimize a quadratic function subject to quadratic constraints. And this problem can be linearized in the lifted space where you have a matrix X, which in your mind, you define it as X times X transpose. And then the quadratic term can be linearized to this Frobenius product, which is the sum of entry-wise products. And then the feasible region can be convexified to this closed convex hull. So you can easily show that the optimal values of these two problems are the same. So well, given that a QCQP is NP-hard in general, so you can't really expect to have a explicit description of the C bar of F for a general F. Right? But the more we know about the C bar of F, the better we can hope to solve QCQPs. If you have a complete description of a certain C bar of F, then you can solve the corresponding QCQP, at least in terms of the optimal value. If you only have a partial understanding of the C bar of F, then well, that can help in some sense to generate valid inequalities of convex relaxations. So some known results are listed here. So when F is composed of a single inequality or an interval bounded inequality, an interval bounded inequality is just like a quadratic function, which is lower bounded by a number A and then upper bounded by a number B. Or when F is defined by a single equality, or when F is defined by non-interacting constraints. So non-interacting constraints here means if one of the constraints that define F is active, then all the other constraints are satisfied strictly. I'll show some pictures later. Okay. In those cases, this closed convex hull can be shown to be equal to the short relaxation, which is a linearized version of those quadratic constraints. Okay. Some other cases include, some other semi-definite representable cases include when F is a low-dimensional polyhedron. So in that case, the closed convex hull is related to the doubly non-negative cone. And when F is defined by a ball constraint and non-intersecting linear constraint, so that's like a variant of the Truss-Friedin subproblem. And in that case, the closed convex hull can be represented by a positive semi-definite constraint and several second-order cone constraints. Okay. So, well, I'm pretty sure this is not a complete list of other results, but well, my understanding is not too many other results exist or are well known out there. So a natural question we ask is, how can we find more explicit descriptions of C bar of F for more general F? The idea is that we could try to mildly add some constraints to known F and see what happens. So we have a simple set F, and then we can try to add, say, one quadratic constraint to it and then see what we can describe for the new closed convex hull. So now we consider another quadratically constrained set. So basically, it's just like a copy of the first set. Well, not really a copy, but they basically play the same role. And we take the intersection of those two. So we're taking the intersection of two quadratically defined sets. It is quite clear to see that the closed convex hull of this intersection is a subset of the intersection of the closed convex hull. Okay. So, well, then a natural question is, when do we have this them at equality? So the main result of this project is that when the W case, which are the Hessians, let me see. So the W case are the Hessians that define the Hessians of the quadratic functions that define H. So when the W case are non-zero, and when H induces non-intersecting constraints in F. So here I'm using non-intersecting, not non-interacting. I'll explain the difference. So here, so this is a definition of the non-intersecting in this project. I mean, there are non-intersecting assumptions elsewhere. There are slight differences, and here is our definition. So here, non-intersecting means that if one of those constraints are active, then all the other constraints are satisfied. They don't have to be strictly satisfied, but they have to be satisfied. So geometrically speaking, if you draw the graph of H, so you can write this H. So H is defined by several quadratic constraints, and if you separate them and define each of them by HK, and you can then this H is just the intersection of those HKs. What this non-intersecting assumption requires is that the boundary of those HKs are contained in the feasible region or in the intersection. Let me show you some pictures. So the first one is this interval bounded case, the interval bounded generalized trust region subproblem. So what this is that you have two like parallel parabolas here. So so you can consider H as the part above this lower parabola, and F as the part that is below this upper parabola. So this is the intersection is the feasible region, and you can see this the constraints are non-intersecting, or actually they are non-interacting. The second example is a more general non-interacting constraint. So basically you can have all kinds of quadratic functions, and then you can take out hollows from it. As long as the boundaries don't touch, they are non-interacting. The third example comes from a previous paper. So when F is bounded, so you have this bounded ball that's F, and then you can take out like bounded hollows from it. Those hollows they can touch, or they can touch the boundary. But so you have like three H's. So H1, H2, H3, and H1 is the set that's outside of this ball, right? And similarly for H2 and H3. So here I have two more interesting examples. The first one is you can have this. So the non-intersecting assumption is only on H. So it says that H cannot be. So the constraints that define H cannot intersect, and H cannot intersect with F. But inside of F, the constraints can intersect. It's okay. So here we can define F as the non-negative quadrant, and then we can take a quadratic hollow from it. So this is an unbounded case, and you can see the boundary of H is contained entirely in this feasible region G. So that's a non-intersecting case. Another interesting example is we can consider this graph. It's just three parallel lines. Okay. Like when you see this, it's like it's probably somehow related to like lattice-free sets. But here the set G. That's defined as just these three parallel lines. And we can consider this as F, which is the area between the first line and the third line. And H1 is the area outside of the first line and the second line. And H2 is the area that's outside of the second line and the third line. So when you take the intersection, you just got these three lines left. You can definitely generalize that to multiple lines. All right. Okay. So the next question is, how can we check these non-intersecting constraints? Well, it can be checked in polynomial time. Don might not agree with this, but you can solve semi-definite programs to check this non-intersecting assumption. So the non-intersecting assumption holds if and only if those QCQPs are give you a non-positive optimal value. And those QCQPs have one quadratic equality constraint. So by the S lemma with equality, those problems can be solved by solving this STP if two-sided Slater's condition. It's like a mild regularity condition. If that's satisfied, then those problems can be solved by STPs. Actually, if they are not satisfied, then the problem is either trivial or like you have some redundant constraints that you can drop. So the problems can be reduced. Okay. So in the next part, I want to talk. So let me just remind us. So what we proved is that when H induces non-intersecting constraints to F, then and WKs are non-zero. The convex hull, the closed convex hull of the intersection is equal to the intersection of the closed convex hulls. Okay. So in the second part, I'm just going to show a sketch of the proof ideas. First, so this is the definition of the convex hull in a lifted space. Okay, so I want to first show the difficulty in this case. So there's a result in the bounded case several years ago, and we were just trying to generalize that to this unbounded case. And what is different here is that like in the bounded case, if the set is bounded, so when F is this a simple example, when F is this interval from -2 to 1, in this case, you see all the extreme points of this set C of F. They lie on the boundary of this parabola right here, and so the convex hull is nicely bounded and closed. So when you want to make some arguments, then you can basically focus on the extreme points. And if you have some properties of the extreme points, you can try to generalize that to this entire convex hull. But when F is unbounded, well, you see one part can go to infinity. So you still have all the extreme points on the boundary of this parabola. But when you connect them, you get a set that's not closed. So this vertical ray is not included in the convex hull. So in that case, if you just have these extreme points, that's not enough to characterize this entire set. We couldn't find an easy continuity argument to discuss this, and also it doesn't seem easy to characterize the extreme rays of such a set C bar of F. So that's the difficulty we encountered at like when we first started the project. Then we found a rescue. So this lemma comes from Dixon and his co-authors. So it's about the conic hull, the closure of the conic hull of a set defined in this special form. And this closure of the conic hull is related to the convex hull of a quadratic form where this y is defined in a modified cone. So don't worry too much about this notation here. Basically, what we interpreted from this, when we tailor that into our setting, what we see is that the closure of the convex hull is equal to the convex hull plus this is the Minkowski sum. Is equal to the convex hull plus this convex hull. The linear part is 0, and the quadratic part is related to this S infinity. And S infinity here represents the asymptotic cone. I'll explain that later. Okay. And from here, we can easily see that this cone is a subset of the recession cone of the closed convex hull. So we don't have a full description of the recession cone of this closed convex hull, but at least we know a subset of it. My guess is this is probably it, but well, we don't have a formal proof on that. Okay, so that takes us to the asymptotic cone. Basically, the asymptotic cone is defined as the set of directions such that there's a sequence in the set, and that sequence kind of approaches to that direction in some sense. You can regard it as a generalization of the recession cone of a set, but it works for non-convex sets as well. And in the same paper, Dixon proves that if a set is defined by a single quadratic inequality, then the asymptotic cones are given by this. So there are two different cases. The first case is when A is not positive semi-definite, then it's given by this quadratic inequality. And if A is positive semi-definite, then the asymptotic cone is like half of that. It's cut by a half space. Okay, so given this, just here's an easy illustration. If you have if your set is defined by a single inequality constraint, so you have a hyperbola here, then the asymptotic cone is just this red area, the asymptotic cone. So with this results, we were wondering like what would happen if we don't have a single equality constraint, but a single we don't have an inequality constraint, but a single equality constraint. It can be regarded as like two constraints. You take taking the intersection of two inequality constraints, but it also has some special structure. So like if you look at this example, then if you change the inequality to equality, then you just have those two hyperbolas. And then the asymptotic cone, it's just this cross. And that's a non-convex cone. Okay, and we managed to prove in general that if S is defined by a single quadratic equality, then the asymptotic cones are given in this four different cases. The first case is when A is equal to 0, and then in that case, this set S is just a hyperplane, just a hyperplane. So the asymptotic cone is also a hyperplane. And in the other three cases, this term, this quadratic equation is involved, and depending on whether it's positive semi-definite or negative semi-definite, it could be cut into half. And with this result, with this result, we can build a connection with Dickinson's result. So here's what we did. Recall that HK, that is the set defined by one quadratic constraint in the newly by one of the newly added quadratic constraint. When WK is not equal to 0, okay, that's like excluding the last case. Okay? When WK is not equal to 0, if D transpose WKD is equal to 0, then we have D is in the union of the boundaries of those HKs. So like this is the boundary, and this is like a mirror, or the symmetric part is just take the negative of that. And when you lift the things from D from this space to the quadratic space, to this DD transpose, then this negative part, the symmetry kind of unify into one set. So in that case, we have this one. On the other hand, the boundary of those HKs, they are in the set G by our non-intersecting assumption. So when you lift this D into the quadratic space, then these two sets kind of unify into one, and you can show that the 0 DD transpose is actually in the recession cone C bar of G. So basically, what that means, with some further arguments, what that means is that if you have a point that's in the closed convex of F, and also a newly added constraint is active, then it is in the closed convex of G. Okay, and so this argument here, or the proof here, is quite similar to the proof of the bounded case, if you're in case you're familiar with the previous paper. So the only difference, so we use a rank 1 decomposition, and the difference is that if the problem is bounded, then the WKs are positive definite, then you can discuss all the extreme points at once. And when this WK is general, and there are some other terms left, and those terms happen to be in the recession cone of C bar of G. And that's like where our lemma is applied. Okay. And with this proposition, we can show that if the constraint is inactive, if all of the newly added constraints are inactive, then we can actually decompose a point here and then take things like make convex combinations around. And then the convex combinations can be shown to be in this set. And that finally proves that this original point is in C bar of G as well. Okay. And with that, we have our main theorem. So when H induces non-intersecting constraints in F and the Hessians that define H are non-zero, we have the closed convex Hall is equal to the intersection of the closed convex of the intersection is equal to the intersection of the closed convex of F and the Schroer-Lixation of H. So Schroer-Lixation just gives you the simple lifted inequality. Okay, and if you take this F here to be Rn, then what we get is basically just the C bar of H equals to S of H. If H induces, if H is like non-intersecting. Okay. And if we combine these two results, well, so we simply just replaces S of H by C of H, then C bar of H, then we get this this final result. Okay. To summarize, so when the Hessians are non-zero and H induces non-intersecting constraints in F, characterizing the closed convex of the intersection is no harder than characterizing the convex Hall itself. You just add in some lifted versions of the newly added quadratic constraints. And this result can be interpreted as a sufficient condition for this equality. The closed convex of the intersection is equal to the intersection of the closed convex halls. The non-intersecting assumption here is relatively strong, and I have to admit that. For example, we can't really characterize a set like this. If F is, this is a very simple set. We have a quadratic, you have the non-negative quadrant, the first quadrant, and then you have x1, x2 less than or equal to 1. So just a hyperbola, one branch of the hyperbola. The reason why we can't characterize this is because for this hyperbola, there's a second branch. And the second branch is outside of this non-negative quadrant. So we can't really say that if you define this non-negative quadrant to be F, then we can't really say that this H induces non-intersecting constraints. So it's actually outside of G. But it feels interesting, and you just wonder what's going to happen in this case. Maybe we can like relax our assumption a little bit to make this one fit. This also opens the door for exploration of more sufficient conditions for this equation to hold. And that's, I mean, there's no way that's easy. We just hope that more and more sufficient conditions can be added, and maybe we can also look at the necessary conditions to rule out things that are not possible. Okay, and that's it. Thank you for your attention. And if you have questions or you have any suggestions, please feel free to contact me in the workshop or after. Thank you.